Now, second part, we will deal with the dynamic excitation, whereas the bridge movement from turbulency and vortex remain limited. The vortices may run onto the bridge for a long time, or the gusts may hit the bridge. There will be a certain movement, and that's it, and it will stay there. With what we deal now, it may go beyond all limits and destroy the bridge. Our third part of phenomena, which is the self-excitation or motion-induced effects. Again, we have this important table showing the three different. Now, the motion-induced, we have rhythmic motion of the body in the flow. It's together. The beam moves, acts together with the surrounding air. It's a combined system, air plus beam. That's the difference to the other two before. And okay, it can be vertical and rotational. Rotational is very important here. And basically, we have the effect of self-excitation stability. And you may always remember that we have here something like a buckling problem in general statics. We have an Euler case 1 where we can have a sudden diversion, Verzweigungsproblem in here, which goes beyond limits and destroys the bridge. This is the second, I would like to say, very important picture I'm showing you and I'm trying to explain. Because on here are, I think in an excellent way, the different phenomena which we have here are explained. First of all, and I told you, the interaction of the air with the beam changes the certain characteristics of the beam. Now, the wind force may act as a torsional spring. We can, if that's our beam, and we can think of the surrounding air as a torsional spring, which with increasing wind speed changes the torsional eigenfrequency of the beam. If we have at wind speed 0 this torsional eigenfrequency, and the wind increases, and we have a cross-section which is sensitive, of course, it depends on the cross-section, then the torsional frequency with increasing wind goes down, goes down. Here we start in a ratio torsional frequency twice the bending frequency. You see? Bending, torsional. And we come to a point where they are identical. Suddenly, we have the phenomenon of flutter, which I will show you in detail. And then the wind goes on, and the torsional spring becomes stronger and stronger, and the torsional frequency goes to 0. And then we have the problem of torsional divergence, which actually is Tacoma. Divergence ist a German Verzweigung. Verzweigungsproblem is a divergence problem. So, wind force as torsional spring. Then we have the wind force as a translational damper, can act as a damper, for vertical movement. Now, a standard bridge beam, in this case, there will not happen much. But you remember I've showed you galloping. That is the effect here. Galloping, I showed you cable galloping, where we have suddenly the change of uplift with increasing wind speed, dc after d alpha becomes 0, becomes negative. Here we see it. And then we come to galloping, which I explained to you. Wind rain we showed. And of course, if we have rather bluff, square bridge sections with little or no cantilevers, that is then sensitive to galloping. And finally, we can have the wind force as negative torsional damping. Here we said a torsional spring, changing the torsional eigenfrequency. Here we have torsional damping, changing the eigendamping of the beam and even increasing, so there is a negative eigendamping. And that shows up, well, I just mentioned it, the Scanlenschen aerodynamic derivatives. In this case, the A2, the very characteristic. It comes up with open cross sections like Tacoma. Here is the Tacoma, and this was the Tacoma phenomenon. The wind around the beam acting together changed or exerted a negative damping onto the beam, and that then made these big movements. So if you want to understand what's coming later again, look through this. It's all explained in many words in the script. Now, I mentioned already self-excitation or divergence on the dynamic behavior. We have here a similarity from buckling problem, suddenly a divergence, Verzweigungsproblem, or if we have an eccentric compression, then we don't have divergence, but we have nonlinear theory of second order increase of stresses. And we have the same here. Under constant laminar wind, in reality, we have a bifurcation, which is again another word for Verzweigung problem. Suddenly the movement goes beyond all limits. Or if we have turbulent wind, not like beautiful and parallel, but like this, like true wind is, then we don't have this divergence or bifurcation, but we just have secondary effects on section forces like buckling problem and stress problem. Instability, we have here the bifurcation problem in laminar wind and the secondary in turbulent wind. It's always a question, of course, what is the required relation between wind on site and the onset wind speed for, say, flutter. This depends, the wind speed shown here depends on the angle of attack. For horizontal wind, the wind speed in reality, in nature, is the biggest, is, say, here, very roughly, or here, speaking. And if the angle increases, then the highest wind speed decreases. And in actual fact, the wind speed decreases more faster than the critical wind speed, say, from flutter. So we can rest assured, if we have the safety here, it will not be worse for angles acting in general. And then naturally we have to multiply our certain wind speed. Normally we take the wind speed for 30 oscillations in the wind with some ultimate factor. Normally we go by for the wind pressure we go by 1.5. Then of course the wind speed is the square root of 1.5 because the pressure goes with the square of the wind speed. So if that's the natural wind speed we have to take into account, then this is at ultimate stage square root gamma, square root times 1.5. We are here. And this may be the onset for some flutter phenomenon, and it must be away from the ultimate wind speed. Now, we like to show some practical examples for bending type galloping. Galloping, you remember, was the transverse movement. If we add up the wind speed and the relative movement, we come to a drift, and we have here the negative branch in the change of the drag factor with angle of attack. That's always when we have that, we know already, aha, here we go. We have to look into galloping. That comes out of a wind tunnel testing. It can happen with bridges, not only with cables. We had a bridge with this unfavorable cross-section, rather narrow, but deep, and an open cross-section here with webs coming down. And what happened was, this was the wind speed in this case for the on-site, which we had to consider. And then in the wind tunnel, we got this speed range for the onset of galloping. And galloping is also a stability case, goes beyond all limits. So, no good. Couldn't build the bridge. So, in this case, Kovacs found out if he placed a damper here between bridge beam and tower, then this damper was enough to increase the required speed for this galloping phenomenon from here to there, and we had sufficient safety. So not only the stay cables can show galloping phenomena, also a beam, especially if it's narrow and deep and has no bottom slab, is open. And here again we have this change of lift with the angle we see here from the wind tunnel. When that came out, everybody said, aha, here we go. Now, what shall we do to get the bridge stable? It also happens if we have a cross-section with the traffic band on. Then we may have a beautiful cross-section here, but if we have the 4-meter high lorries on, suddenly we have a galloping prone cross-section with traffic on. And it shows here the red one, and the second effect, I just make it simple, is if we have a cantilever, then it's much better against galloping than without a cantilever. And it shows here the red ones, the red curves, again, drag versus angle. The red ones, which are bad with a dip here, are those without cantilevers, and the green one are those with cantilevers. Of course, with the high traffic band, it's much more distinct than here. But cantilevers are important, and we must think about the traffic band. And I give you a hint. We had a problem once with the traffic band of a railway. And if you have a long railway and say, well, the motor may break down in the middle of the bridge, and so it stands there, and then you have a problem. Sarate-Brasilago bridges, well, I can't go into here, but I just tell you it's not only the cross-section. We must consider the traffic band on it, and how long as it is there, it's all probability calculations. Okay, we can also have galloping phenomena at the tower. We have here the example of the second Panama Bridge. You may remember I've shown it. This is a cross-section of a tower leg, the wind blowing, and here we have our diagram, drag or factor versus angle. And you know already and say, here we go. What shall we do now? Now, we could build the bridge as it was designed because the eigendamping of the concrete was just enough to suppress this system which showed up for an undampened cross-section in the wind tunnel. So there we didn't have to do anything. There are other examples, Vladivostok, Golden Ears Bridge, where this didn't work, steel towers, low internal damping. There we had to put tuned mass dampers into the tower legs. Can also happen with the towers. Okay, now we come to torsional galloping. Torsional galloping, you may remember the frequency and the damping is changed, and the torsional galloping, as shown here for this bridge, a true bridge, it was Ting Kau in Hong Kong, is very much depending, or can depend, on the edge configuration of the beam. And I tell you straight, it's not completely understood why this is so. We can just state what shows up in the wind tunnel. Just for this bridge, look at the two cross-sections. The only difference basically is that we have here a short cantilever with a short fascia of 0.5 meter depth. And here we have basically the same, but a 1 meter deep fascia. And whereas here the critical wind speed was 67 meters per second, this was 92. That's 50% more. And I wouldn't dare to tell you, well, that was easy to be foreseen. It must be like that. No, we just have to go into the wind tunnel and then look into these. You see, this wind nose, which was investigated, gave only 18 meters per second critical wind, whereas this little fiddle here gave us 92. There are things in aerodynamics which are still not known, and therefore we use wind tunnel tests and just try and vary the edge configuration and hope for the best, that we hit the good one, but it's not really completely known and understood mathematically why this happens. You can simulate it in a computer, but behind it, the deeper reason, we just don't know. Now, a very interesting example is the pedestrian bridge across the Rhine River, Strasbourg-Kehl. Now, we have here 183 meters. It's a true Rhine River bridge as a pedestrian bridge, which is very unusual for us. We were very daring to do that. It's a very light bridge. It worked. Got the German Bridge Prize for that and all that. And it has two superstructures. One from here up, down, connecting the river walks close to the water, say in summer. But if we have high water, then we need also a connection from the top of the levees here from both sides. So there are two separate cross-sections, more an arch type and a higher up one, meeting in the middle, and we have here the lower one, the upper one, if we take a section here, and we have a void. All very light, only pedestrian loads, steel cross-section. It's a very light bridge. And now, there then we have the interesting phenomenon. For a certain wind speed, we and the torsional mode of the structure of 0.65, we have the phenomenon that the wind comes from here and forms a vortex. You know, it's an obstruction in the wind here. So, and at this situation, for this given wind speed, the length of the, say, the wave, of course, changes with wind speed. And for the wind speed of 13.5 meters per second, we just have the wind attaching here, going through and reattaching at the second beam, which of course gives us a torsional impact. And if we go again into our diagrams, I can't help it, you must try to understand them sometime. Then we have here, it's not shown, that's a speed of 13.5 meters here. And that's the torsional frequency of 0.65, which we have here. And then we are just at the internal structural damping of 0.04. That's just eaten up. The steel has an eigendamping less than concrete, but still it's there, 0.04. And this hitting here acts like a negative damping from the air. And so at this point the eigendamping is just eaten up, and there is negative damping from this interaction from the wind with the beam. And of course the bridge would be unstable. It would, the A2, I just make it briefly, had this hunch here. It's this downward again. So what to do? Now, there was no way around then to dampen, I just say it. We used a tuned mass damper, TMD. In German it's Tilger. Kein Dämpfer, not energy consuming, but a Tilger, tuned mass damper. And torsion, I showed you why. Hitting here and there. Now that gives us a torsional divergence problem. There were two, I just call it like seesaws. On a, if kids play and sit on a seesaw on a swing and go up and down, that's the type of tuned mass damper against, it's a torsion tuned mass damper, like a seesaw. Here, of course, with the proper weight and friction and so on. And now with this arrangement, the bridge could be made stable. However, it is rather complicated, this type. So we said, or Kovacs said, what happens if these seesaws do not work as considered? Does then the bridge come down? I mean, we cannot accept that possibility. Whatever happens, I mean, the bridge must remain stable. There may be movement or so, but it must come down. So it was then considered that one tuned mass damper is stuck, doesn't work at all, and the other one is out of tune by 10%. Now, what happens then with the bridge? Mr. Depe will show us. So Kovacs had the thing running in a time history, and with these out of tune, one not working at all and the other out of tune, and the result was, okay, there are exaggerated here in the film movements, but still within the acceptable range. So even if these dampers do not work as expected, the bridge will not come down. And that's what we, of course, have to ascertain if we go into more sophisticated damper things and so on. What happens if it doesn't work? If it's not inspected properly and things like that. Okay? Now we come to maybe the best known phenomenon, flutter. Tacoma is often said to be flutter. It's not, but that's a very fine point. And we can, it's of course very well known because we can calculate it rather easily with the help of Kloppel-Thiele method. Now, what is flutter? I would like that you try to understand that. That's not just some mathematics, long formula where you put some figures in. But what is the phenomenon? And it is easily to understand. I try at least to explain it to you. Now, we have, I mentioned it in the big overview, and I repeat it now. We have here the wind speed, and we have here the bending vertical movement frequency, and we have the torsional frequency. And for no wind, the torsional is rather big, say about 2 times the bending. Typical bridge, and if the wind blows with small, reasonable speed, nothing happens. However, if we have a cross-section, not the calculation is made for an airfoil, flat plate. If we have a reality cross-section, then we have the wind acting as a torsional spring, reducing, with increasing wind speed, reducing the torsional frequency. And after some time, at some wind speed, we have the same torsional frequency as bending frequency. And then this phenomenon can come on, which I think explains very nicely how, in this case, for identical bending and torsion frequency, the energy is taken out of the air into the structure, and with time making it explode beyond all limits. You see, we start here from the left. We have the beam at a certain angle. The wind blows, drives it up, and then the bending gets it up, and the torsional frequency at the same time, which are identical, changes it down, so the wind now blows it down. It's horizontal. Again, the torsional has now changed the direction, so the wind is blowing up and down. You see it here. It's, of course, at one place. It's just with time. We start here. The wind with 45 degrees, wind blowing, drives the beam up. Now, the bending frequency is this. The torsional frequency is this. Once we are here, it's horizontal, and the torsional rotation gets it down. So when we are here, we are again at 0. The wind pushes it down. Again, here pushes it up. So with this, just at the same time, at the right time, the rotation changing the wind, the direction of the beam, such way that the wind is blowing it up and then pushing it down again. And that, of course, only works if the torsional and bending frequency is identical. If they wouldn't be identical, then at this place maybe it would blow it up and so on. So that's the mechanism behind flutter. And you can see if that goes on with every movement, there is energy, there is a kick is given, energy is pushed, is pulled out, and the movement goes beyond all limits. That's the flutter phenomenon. I think that you should try to think through. After I saw, after some time, this diagram, I said, now I understand. So hopefully you come to the same moment. Okay, now, Kleber Thiele initially goes with double interpolation and all sorts of things. However, one could simplify the whole thing, and so it's fairly easy these days to calculate the critical wind speed, and it depends on the beam. Basically, it's the beam width and beam bending frequency. There's the ratio of the frequencies, and of course there is some mass and so on in. But all this would be the critical wind speed for the onset of flutter for a given ratio for this type of airfoil. Now, in reality, we have a real bridge beam, and there is a reduction for a real bluff bridge beam, which has some shape instead of a flat slab, even if the bridge beam has the same frequencies and mass distribution and so on, and that's given in a reduction factor eta. And Kloeber-Thiele had evaluated a great number of wind tunnel tests and shown, and there are several diagrams in the publication, it's still okay, where for a given ratio of bending to torsion, we are normally here between 2 and 3, and certain shapes. He had calculated, or rather Mr. Thiele had calculated, the theoretical flutter wind speed, and then they compared that with, for this cross-section, the flutter wind speed in the wind tunnel. And without fail, that was lower, and so they tabulated that in the range of here. If we have a flat slab, then the reduction factor is 0. And our true cross-sections, and I've given just a few examples here, are in this range. So we are somewhere 0.5. So our true cross-sections have a onset flutter wind speed of about 1/2 of the flat slab, so the shape factor is about 1/2. And in the script, and I've also lectured on it, is an example where I calculate the flutter wind speed for a given cross-section. It's called example for a long span cable stayed bridge. So there this formula is used, and if you wanted to look it up, how there is a calculated example. Well, in the book I know it's section 4.5. I've just completed it for the printer. Okay. So flutter, you remember here this blowing up and down. Thank God Kloeber-Thiele found a method, and there is a simple way to put it in, and it gives you a rather good result. With all the high tech computer methods, Kloeber-Thiele still is okay. The eta factor, the reduction factor, is a little bit, but otherwise it's well known. Now in Cheon, we had the problem that for the original cross-section, very bluff, the onset wind speed for flutter was down here. In Cheon is in Big Bridge in Korea. And this was required, and with a change of the wind nose here, it was made okay, but mainly I wanted to show you with this film here that today we can even, until now I said, okay, we use the wind tunnel for getting the cross-sectional characteristics and then put that into the analytic computer investigation to go on. We can even omit the wind tunnel and try to get the results from a, say, finite element method with a computer. It's still not 100%. I still prefer to have it checked in the wind tunnel. But it's helpful to change, to look what edge configuration may be helpful and so on. Now, let's see how the airflow is, say, with a sort of finite element analytical method. You see? That's how the bluff initial section had visualized the flow of forces, and of course all the factors and dynamic behavior was taken out there. This is possible We've done it, but again, sometimes it's still better to have a small model in the wind tunnel to check what comes out there. But this is purely theoretical. Okay. Now, we come to wind tunnel testing, which I mentioned to you before. When I talk of wind tunnel testing, I normally refer to what we call a section model to put into the tunnel. Ein Teilmodell, a section model. You see it here. It's part of the bridge beam in a scale, say 1 in 20 or 1 in 30, 40, 50, not more. There are also wind tunnels these days 40 meters long in Denmark, in Lyngby, was done for the Great Belt Bridge, and there's one in Japan done for Akashi Bridge, something like 40 meters. And people put in a full model there. And I always think that's more for show, because the scale is so much different that you cannot get any aerodynamic similarity. It's normally required by clients who don't understand the aerodynamics. And what the aerodynamic people explain to you, like I do today, but for a bridge, they say, well, you know, he can tell us a lot. Well, let's put it into the wind tunnel. And then it's tuned the way that it comes out the right, and everybody's happy. But the scale is too different from reality. That's why section models in this part of the bridge beam, at least the length 6 times the depth or something like that. That's fine. But not the full models. That's cheating yourself. We can either rigidly support the model and rotate it, and then there are scales, of course, and we can measure the forces. So we get the lift, drag, and rotational characteristics out. So we don't change the wind speed, of course, but we rotate the model to get a different angle of attack. We can also elastically support the beam, as indicated here, with springs. The springs tuned in such way that the model has the correct eigenfrequencies, which is a little bit tricky, and you have to take the scale. I'm not going into that, the scale to reality into account. But there are excellent people doing wind tunnel tests, and they know. And then you can also get out the dynamic phenomena, and you can find out what I showed you, the movements from, say, vortex shedding you get, of course, the dynamic limit. I showed you examples. So static values and dynamic values you can get out of a model, it being either rigidly supported for static forces, lift, drag, or elastically supported for turbulence, vortex, and dynamic effects. As I said, we get here the drag factors out, static. The wind, the rotation is normally between plus minus 12 degrees at 1 or 2 degrees steps. And we get, of course, aerodynamic coefficients. You remember the dc by d alpha, that galloping phenomenon we can get out, and for the lift force gradient there. Now, we've shown it briefly, but basically we have here the plus minus 12 degrees, and here we have the drag factors, and we normally calculate it by C, you can do it as you like, the C times the wind pressure, either times the depth or the width. You have to look carefully what is referred to. Somebody refer it to the depth, others refer it always to the width. It's a factor of 10 or so. You'll find out pretty soon if you made a mistake there. And there is a difference whether we have smooth wind, laminar wind, where all the molecules run in parallel, Reynolds 10 to the power of 5, it makes the difference. Whereas we can have smooth flow in the wind tunnel, in reality we hardly ever have it. Therefore we can also do turbulent flow by having a mesh in front of the flow to get turbulence. And then we get this curve, same for torsion. Generally we can say, if we make wind tunnel tests in smooth or laminar flow, we are on the safe side against reality, because the turbulency will always suppress a little bit the phenomena. So again, if we have the wind tunnel test, laminar, which is the simplest and the cheapest, it's all a question of cost, and everything is fine, hook it, beautiful. If it doesn't work, well, then you may say, well, in reality we have some turbulency, let's do the same in turbulency. Maybe that helps already, especially with vortex shedding, and so on. Here I have the printout again from a wind tunnel test. And I just show you, see we have this model here, and we let the wind blow and we measure the forces or the movements. Here we have measured the movements, increasing wind speed, and here the movement. As I said, suddenly at low wind speeds we have some, okay, you would know, no problem, that's vortex shedding, probably doesn't occur. Let's worry about it, I've told you. But it shows, first of all, up, and it's in the wind tunnel report, and everybody may get excited. Whew. Well, it's not so bad. Then you go on, very little happens, and suddenly it explodes. And then you have reached flutter. That is the difference. This is maybe significant movement, but it's limited. You may let the wind blow here at this station for a longer time. There may be lock-in and all sorts of things, but it will normally remain within limit. Here, however, when you hit the flutter, it's like a buckling effect. Suddenly you have a divergence, the thing explodes. And then all these wind tunnel people, they run and try to save their model, because if they don't hold it, the thing really explodes. And they want to save their beautiful handiwork. I've seen it. And they increase the wind speed initially very slowly until they know where the thing really starts, we can also put, say, towers into the wind tunnel to find out the wind loading. Normally what we do is we measure the moment here and then can calculate back what the wind load is and so on. Now, you may say, why that? We know DIN 1055 gives us longitudinal wind, drag factor of 2, I say, and some shading, and this way we know all about it. Yes, but we don't know what happens with the wind in between 0 and 90 degrees. Quarterly wind, 45 degrees is one thing, but there may be even a worse situation with some 15 degrees, whereas when you have transverse wind, the code for this tower tells you nothing happens with the second leg. It's in the shade of the first. But what happens if you have 15-degree wind? Then it's in there, and that may be governing. And so that's why we used here for the Baytown Bridge this model, rotated it through the wind, and then got out the base moment things and could calculate. And in actual fact, the biggest were not at 0, but were at some angles in between. Just be careful there. Don't trust them codes. They make it rather simple. For small bridges, doesn't matter. But for big ones, you have to be careful. Now, wind tunnel tests. I mentioned it before. We use partial models, section models in the wind tunnel to get out the characteristics, lift, drag, and moment, which are unique to this cross-section. It's different for every cross-section. I showed you how sensitive it is to small, changes there. You can change all that. There you are on safe ground. The scale difference is not so big, and we have at least 50 years of experience. We are on safe ground. We know when we use these wind tunnel results it works. Now, when we come to the full bridge, there, I say today, there we use the mathematical or computer analytical model. We use as an input the wind tunnel test results, but to go on with them to find out what it does to the complete bridge, that we do on an analytical model. We do not try to put a full bridge model, even if it's 40 meters long, into the wind tunnel, because the difference in scale, Reynolds, Fraude, I'm not going to tell you all these things which are there important. We just cannot do. It's always a compromise. And in the analytical model, and I've shown you that for Helgeland Bridge, where we did it, Kovacs developed that part of it for the first time there. We can not only have the scale effects omitted, of course, but we can go to nonlinear behavior. We can formulate that the beam, that for a certain situation we check the beam, see it is cracked. When it is cracked, we can reduce the stiffness, have a changed eigenfrequency, run the thing again, and so on. We can iterate even nonlinear effects, say in the beam and otherwise. So it's the best we have. Section model to take out the section properties, analytical model to find out the behavior of the full bridge. Okay, sum it up. You should know this diagram by heart already. I've told you about the 3 most important aerodynamic phenomena or wind-induced vibrations. Number 1 is turbulence-induced. There we just have the bridge with, say, a very smooth, nice cross-section in the wind, and the wind hits it with different gusts. We had that for the Helgeland Bridge. You may recall it comes again, very slender bridge in a very strong wind climate, Norway at the polar circle. There we had very strong winds, and we had a mountain range called the Seven Sisters, a mountain range from where the wind predominantly came, which gave us a turbulence of 25%, which is a hell of a lot. Otherwise you get 5 to 10. So we had high wind speed, 270 kilometers per hour was our design wind speed, plus 25% turbulency. And the governing loading for this bridge was turbulence. So if you have a real bad wind climate, it's not always here the flutter phenomena. It can be just simple the wind blowing against the bridge with gusts. So then we have vortex. behind a black body, vortices form shed in frequency, Struhal number. If the frequency coincides with the eigenfrequency of the beam, we are in resonance, and the small forces which occur when the vortex goes up, down, and here, they just add up, and it is more a statical problem. We have movement there. However, what shows up beautifully in wind tunnels very often does not show up in reality, because the wind is more or less turbulent. The lengths where the vortices attach themselves or detach them from the beams are different, and so on. So very often in reality the wind is turbulent, too turbulent to give the phenomenon which we see in the wind tunnel. And now the real bad one, which can destroy a bridge, are the motion induced. And there we have to remember, it's not like in the other two, the wind exerting forces onto the bridge, which we can simulate with static, with equivalent static loads, and so they remain within a range. Here we have acting together the air body around the beam and the beam itself. And the air body can influence the beam either by introducing negative damping. So whatever eigendamping is there to suppress phenomena is taken away, and the other way around. Or it can reduce as a torsional, additional torsional spring, the torsional eigenfrequency of the beam. For example, in such way that the difference between the torsional frequency and the bending frequency for a regular bridge disappears in that way that the torsional frequency goes down to the bending frequency. And then we have the phenomenon, you remember, the wind blowing up and down, of flutter, where the wind, when they go in the right frequency, goes it up and down. And it may go beyond all limits. Remember the technicians in the wind tunnel getting hold of the model. That's it. And finally, if we do tests in the wind tunnel in laminar wind, we are always on the safe side against the real, more or less turbulent wind in reality. Thank you very much.